There is more to space than you can reach, more directions than any hand can point, more geometry than any eye can follow. Welcome to the Sleepy Lab. Tonight, you will drift through the hidden architecture of space itself, through dimensions folded so small they vanish from sight, and through the quiet mathematics that first suggested they might be there. If you find this a restful place to spend your nights, consider subscribing, one sleepy soul at a time. Now, let's begin. Right now, lying still, you exist in three directions: forward and back, left and right, up and down. These three dimensions are so familiar they feel like the whole of reality, like the complete inventory of what space is allowed to be. But there is a possibility, quiet, persistent, and taken seriously by careful physicists, that the inventory is not complete. That space has more directions than we can point to, more geometry than we can enter, and that those hidden directions may be the very reason the world around you has the particular shape it does. The story begins in 1919. A mathematician and physicist named Theodore Kaluza was working through the equations of general relativity, Einstein's description of gravity as the curvature of spacetime. Kaluza did something simple, in the way that only the most consequential ideas are simple. He added one more dimension to the equations. Not to describe anything he had observed, not because an experiment demanded it. He simply asked what would happen if space had four spatial directions instead of three. And something extraordinary fell out of the mathematics. Maxwell's equations, the complete description of electricity and magnetism, emerged on their own, unbidden, from the geometry of a space with one extra direction. Gravity and electromagnetism, two forces that had seemed entirely separate, turned out to be facets of the same geometric structure, if that structure had one more dimension than we can see. Kaluza wrote his findings in a letter to Einstein. Einstein read it, and then he sat with it for 2 years. 2 years of uncertainty, not dismissal, but genuine hesitation at the border between physics and pure mathematics. He was not sure whether Kaluza had discovered something real about the universe or had found a beautiful coincidence hiding inside an equation. Eventually, Einstein agreed to help publish the work. The idea was too elegant to leave in a drawer. But a question remained, and it was not a small one. If a fourth spatial dimension exists, where is it? Why can nothing in our experience reach it, point along it, or feel its presence? The answer came a few years later from a Swedish physicist named Oscar Klein. Klein proposed that the extra dimension Kaluza had imagined was not open and extended like the three we inhabit. It was curled, folded into a circle so extraordinarily small that nothing we have ever built could resolve it. Klein estimated the radius of that circle to be near the Planck length, roughly 10 to the power of -35 meters. A number so far below ordinary experience that it resists any honest attempt at comparison. But here is one attempt. Take a single atom, already invisible, already smaller than anything the naked eye can register. Now imagine scaling that atom up until it fills the entire observable universe, every galaxy, every filament of dark matter, every void between the clusters of light. At that scale, the Planck length would still be smaller than the atom you started with. That is where the extra dimension lives, if it exists. Coiled at a scale so remote from ordinary measurement that it has never been directly observed and may never be. And yet, this is not quite as strange as it first sounds. Think of a garden hose seen from a great distance. From far away, it looks like a line, one-dimensional, a thread stretched across the grass. But move closer, And the hose reveals its second dimension, its circular cross-section, the direction that wraps around its surface. That direction was always there. It was simply too small to see from where you were standing. A dimension curled into a circle smaller than the Planck length would behave the same way. From any distance larger than the circle's circumference, which is to say, from any distance a human instrument has ever probed, it would look like a point. Not a small circle, a point. The dimension would be there, woven into the fabric of every location in space, and yet effectively invisible. Present in every cubic centimeter of the room around you right now. And entirely beyond reach. This is the Kaluza-Klein picture, the first serious proposal that space might have more dimensions than 3, and that the extra ones hide by curling into themselves at scales too small to enter. It was not taken as established fact. It was not even widely accepted for decades. But it planted something in the soil of theoretical physics that would not stop growing. The idea that the geometry of hidden dimensions could determine the forces we observe in the visible ones. That electromagnetism might not be a separate thing from gravity, but gravity seen from a slightly different angle, an angle we cannot quite turn our heads to face. There is something quietly remarkable about that. The forces that govern every interaction in your body right now, the electrical signals moving through your nerves as you settle towards sleep, the electromagnetic bonds holding every molecule in place, may be echoes of a geometry you cannot enter. Shadows cast by a shape that exists in a direction with no name in any human language. Kaluza found that shape in an equation. Klein suggested where it was hiding. And the universe, as far as we can tell, has not yet confirmed or denied it. It simply continues, folded and patient, in however many directions it actually has, which may be more than 3, and which, tonight, you can let yourself rest inside without needing to count them all. The process of folding those extra dimensions into shapes too small to see has a name in physics: compactification. It is a quiet word for something almost impossible to picture. The idea that a dimension, a full direction in space, could be curled so tightly upon itself that it vanishes from ordinary experience entirely. Not destroyed, not absent, simply folded. The way a vast sheet of paper, rolled into a cylinder, thin enough, begins to look like a line. And the shape into which a dimension is folded is not a trivial detail. It is, in a sense, everything. The geometry of the compactification determines which physical laws emerge in the dimensions that remain large. Change the shape, and you change the forces. Change the curvature, and you change the masses of particles. The hidden geometry is not decoration. It is the source code. This is where string theory enters the picture. String theory, in its most mathematically consistent form, does not work in 3 spatial dimensions. It does not work in 4 or 5 or 8. The mathematics becomes inconsistent, riddled with infinities that cannot be removed, unless the theory is allowed to inhabit exactly 10 space-time dimensions, 9 spatial and 1 of time. That is not a choice the theorists made freely. It is what the equations demanded. And then there is M-theory. M-theory is the framework that drew together 5 separate and competing versions of string theory, each of which had seemed like a different proposal about the fundamental nature of reality. In 1995, Edward Witten showed that all 5 were facets of a single, deeper structure. But that structure required 1 more dimension still. 11 space-time dimensions in total, 10 of space, 1 of time. What the M stands for is genuinely, not settled. Witten himself left it open. Membrane, perhaps, or mystery. or simply M, a placeholder for something not yet fully named. There is something fitting about that. A theory that reaches toward the deepest structure of reality and at its center holds a letter without a word. To understand what string theory is actually proposing, it helps to set aside the image of particles as tiny spheres. In the standard picture of particle physics, an electron is a point, a location with no size, no internal structure, no extension in any direction. String theory replaces that point with something that has length, a loop or strand of energy, one-dimensional, vibrating. And the vibration is the particle. An electron is not a different object from a photon or a quark. It is the same kind of string, vibrating in a different mode. The way a single guitar string, pressed at different points, produces different notes. The fundamental objects of string theory produce different particles depending on how they oscillate, different frequencies, different energies, different masses and charges. All of matter. In this picture, is music played on strings too small to see? The strings themselves are thought to be near the Planck length in size, which means they are, for all practical purposes, unimaginably small, far beyond the reach of any instrument we have built or could build with current technology. Their existence is inferred from the mathematical consistency of the theory, not from direct observation. And those strings need room. Not just the 3 dimensions of length, width, and depth. They need the full 10 dimensions the theory requires to remain consistent, which means 6 spatial dimensions beyond the 3 we experience must exist somewhere and must be hidden. The hiding place, in string theory, is a class of geometric objects called Calabi-Yau manifolds. The name comes from 2 mathematicians, Eugenio Calabi, who in the 1950s conjectured that certain complex geometric spaces with specific curvature properties could exist, and Xingtong Yau, who proved in 1977 that Calabi's conjecture was correct. The spaces Yau confirmed are now called Calabi-Yau manifolds, and they became, years later, the natural candidates for the hidden geometry of string theory. A Calabi-Yau manifold is not something that can be drawn or held in the mind as a clear image. It exists in 6 real dimensions, which means it cannot be fully visualized by a mind that evolved to navigate 3. What can be said is that it is a smooth, closed geometric space with a very particular kind of curvature. A curvature that satisfies conditions related to a property called Ricci flatness, and that this curvature is not uniform but intricately folded with holes and handles, an internal structure that varies from point to point. The shape of that structure is not arbitrary. Each distinct Calabi-Yau manifold produces a different set of physical laws in the large dimensions, a different number of particle families, different masses, different force strengths. The 6 hidden dimensions are not passive background. They are active participants in the physics of the world we can see. Think of it this way. If you lived on the surface of a sphere and knew nothing of the 3rd dimension, you might still notice that parallel lines eventually meet, that the angles of a triangle add up to more than 180 degrees. The hidden curvature of the surface would leave its mark on the geometry you could observe. In the same way, the hidden curvature of a Calabi-Yau manifold leaves its mark on the particles and forces of our 3-dimensional experience. The electron has the mass it has, partly because of a shape we cannot enter. The charge of a proton is what it is, partly because of a geometry folded into dimensions we cannot point toward. There is a long stillness in that thought. All the familiar constants of the physical world, the numbers that appear in every equation of chemistry and biology, and the slow electrical rhythms of a resting brain, may be consequences of a shape chosen, or perhaps simply occupied, by the particular compactification our universe settled into. And there are many possible shapes, The number of distinct Calabi-Yau manifolds that could, in principle, serve as the hidden geometry of string theory is estimated to be something like 10 to the power of 500. That is not a number that corresponds to anything in ordinary experience. It is larger than the number of atoms in the observable universe by an almost incomprehensible margin. Each one a different possible universe, a different set of constants, a different arrangement of forces. Most of those universes would not permit atoms to form. Most would not permit stars to burn long enough for planets to cool. Most would not permit anything as intricate as a cell, or a thought, or a quiet breath taken in the dark before sleep. But some would, and we appear to be in one of them. Whether that is because our particular Calabi-Yau shape was selected by some process, or simply because only certain shapes permit observers to exist and ask the question, that remains genuinely open. It is one of the deeper puzzles sitting at the edge of what physics can currently say. For now, the manifold is a mathematical object, beautiful in the way that precise and intricate things are beautiful, studied by geometers and physicists in a collaboration that Calabi and Yau could not have anticipated when they were working on curvature conditions in the 1950s and 1970s. The universe, it seems, had already decided to use their work. It had already folded itself into a shape they were only beginning to describe. And somewhere inside that folding, in the 6 directions you cannot move, the 6 dimensions curled smaller than any instrument can reach, the particular world you inhabit was quietly being determined. The mass of your body, the light that enters your eyes, the forces that hold every atom of you in place as you rest here now. All of it shaped by a geometry with no name in the language of the senses, only in mathematics, only in the patient, unhurried language of curvature and dimension and form. And so the geometry does not end there. The 6 curled dimensions have a shape, and that shape matters enormously. But which shape? That is a question the mathematics alone cannot answer. The number of distinct Calabi-Yau forms that could in principle serve as the hidden architecture of string theory is estimated to be something like 10 to the power of 500. That is not a number that has a comfortable analogy. 10 to the 500 is larger than the number of atoms in the observable universe by a margin so vast that the comparison itself becomes difficult to hold. Each of those shapes is a valid solution to the equations. Each one is geometrically consistent, and each one would produce a different universe. Not different in small ways, different in the ways that matter most. A different Calabi-Yau shape means different particle masses, different values for the fundamental constants, different strengths for the forces that hold matter together. In some of those universes, the particular balance of forces that allows a hydrogen atom to be stable would not exist. In others, atoms might form, but only a handful of varieties. The periodic table, with its quiet rows of elements, is not a universal given. It is a consequence of geometry, of the specific curvature of dimensions too small to see. This vast collection of possible universes, each arising from a different compactification, each with its own physics, is sometimes called the string landscape. The word landscape is chosen carefully. It suggests terrain, high ground and low ground, peaks and valleys. Each valley is a stable configuration, a place where the geometry settles and the physical laws crystallize into a particular form. Our universe, on this picture, occupies one valley among something like 10 to the 500. Whether that is a satisfying answer or a deeply unsatisfying one depends on what you were hoping physics would tell you. Some physicists find the landscape troubling. If the theory permits so many possible universes, it seems to lose its power to predict which one we should find ourselves in. Others find it clarifying. The question shifts from, Why do the constants have these values? To which of the many possible configurations permits the existence of something that can ask the question? That second framing has no clean resolution yet. It sits at the edge of what current physics can say, and we will return to it, gently, a little later. For now, there is another question the landscape touches, a question that was already pressing before string theory arrived. It is called the hierarchy problem, and it concerns something quietly strange about the world you inhabit. Of the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, gravity is by far the most familiar. It holds you to the Earth. It keeps the Earth near the Sun. It shapes the large-scale structure of everything we can observe. And yet gravity is, by an almost incomprehensible margin, the weakest of the four. Roughly 10 to the 37th times weaker than electromagnetism. That is not a small difference. That is a difference so large it has no comfortable name. If you hold a small magnet near a pin, the electromagnetic force of that magnet, acting across a few centimeters, overcomes the gravitational pull of the entire planet beneath the pin. The whole Earth pulling down, and a small magnet pulling up, and the magnet wins. Standard physics has no satisfying explanation for why this should be so. The equations accommodate the disparity, but they do not explain it. The numbers have to be inserted by hand, carefully, precisely, in a way that feels less like a discovery and more like a correction. This is what physicists mean when they call it a problem. Not that the theory fails, but that the theory requires something that looks like an unlikely coincidence without offering a reason for it. One proposed resolution is quiet in its elegance. Perhaps gravity is not intrinsically weak. Perhaps it only appears weak because it is being diluted. The other forces, electromagnetism, the strong force, the weak force, are confined. They act within the three large dimensions of space and do not spread beyond them. But gravity, according to several extra-dimensional models, is not confined in the same way. Gravity may leak. It may spread not only through the three dimensions we inhabit, but also into the additional dimensions beyond them. And in spreading further, it arrives at any given point in our space diminished, thinned across a larger geometry. On this picture, gravity is not weak. It is simply elsewhere, in part, distributed across a space we cannot enter. This is a different kind of answer than physics usually offers. It does not say the constant has a particular value because of some symmetry or some deeper principle. It says the constant appears to have a particular value because we are measuring it from inside a limited portion of a larger space. The weakness of gravity becomes a geometric effect, a consequence of where we are, rather than what gravity fundamentally is. To make this precise, physicists developed what are called Brane world models. The word Brane comes from membrane, and the idea is that our observable universe, everything we can see, touch, measure, or move through, is a three-dimensional membrane embedded in a higher dimensional space. That higher dimensional space is called the bulk. Our brain floats within it, or rests within it. The spatial metaphor is imperfect, because the bulk is not a space we can point toward. It is not above or below or in any direction the body knows. It is a direction that simply does not exist for us, a dimension the senses have no organ to detect. The matter and forces we are made of, the atoms, the light, the electromagnetic fields, are bound to the brain. They cannot leave it. They propagate along its surface the way ripples propagate along the surface of water, unable to detach and travel through the air above. But gravity is different. Gravity, in these models, is not confined to the brain. It propagates through the bulk as well, and so it spreads into dimensions that the other forces never enter. By the time it returns to act within our brain, it has been diluted by the geometry of the bulk. And what we measure as the weakness of gravity is the residue of a force that has been spreading through a larger space. The brain is not a metaphor. In the mathematics of string theory, brains are genuine objects, extended structures on which strings can end. They have tension. They can carry charge. They interact with one another. Our universe being a brain is not a poetic image, but a specific physical proposal with equations behind it. And the bulk surrounding it, that larger space, is not empty in any simple sense. It has geometry. It has curvature. It may contain other brains, separated from ours by distances measured in dimensions we cannot cross. There may be matter on those other brains, structures, fields, configurations of energy that we will never see directly. Not because they are far away in the ordinary sense, but because they exist in a direction that our instruments, our bodies, and our senses have no way to face. The only force that might carry a signal between brains is gravity. And gravity, as we have just said, is very quiet. So the universe may be less empty than it appears, and the silence around us may not be the silence of absence, but the silence of a geometry that keeps certain things permanently, softly, out of reach. And the word itself carries a quiet history. Brane, it comes from membrane, that thin, flexible boundary that separates one region from another. In biology, a membrane is the edge of a cell, the place where inside becomes outside. In physics, the meaning stretches further. A brane is any extended object with some number of spatial dimensions. It can have one dimension, like a line, 2 dimensions, like a surface, 3 dimensions, like the volume we inhabit, or more. The mathematics does not insist on any particular number. It only asks that the object be extended, that it have some geometry, that strings be able to end on it. Our universe, in this picture, would be a 3-dimensional brane, a specific kind, sometimes called a 3-brane, embedded in a space with at least one additional dimension beyond our own. And the question that follows naturally is this: if there are extra dimensions surrounding our brain, why have we never noticed them? There are 2 broad kinds of answers. One says the extra dimensions are too small to see, curled into shapes far below anything our instruments can probe. The other says the extra dimensions might not be small at all. They might be large, even very large, and we have simply never had a way to look into them. That second possibility is stranger than it first sounds. In 1998, 3 physicists, Nima Arkani-Hamed, Savas Dimopoulos, and Gia Diwali, proposed something that seemed almost too simple. They suggested that extra dimensions could be as large as a fraction of a millimeter, not curled to the Planck scale, not hidden in some impossibly fine geometry, but genuinely large by the standards of particle physics and still completely undetected. The reason this is possible comes back to gravity. Gravity is the only force, in most extra-dimensional models, that can travel freely through the bulk. The other forces, electromagnetism, the strong force, the weak force, are confined to the brain. They cannot leave. Their fields are anchored here. But gravity is different. Gravity, in these models, propagates everywhere, into the brain and out of it, into the bulk in all directions. And this means that if you are testing gravity at large distances, across a room, across a solar system, you are testing it in a regime where the extra dimensions are effectively invisible. The gravitational field has already spread so far that the small additional spreading into a compact extra dimension makes no measurable difference. But at very short distances, at scales comparable to the size of the extra dimension itself, the behavior of gravity would change. Newton's inverse square law, the rule that gravity weakens with the square of the distance, holds in 3 spatial dimensions. In a space with more large dimensions, the force would fall off more steeply. It would weaken faster. And if you could measure gravity precisely enough at short enough distances, you would see the law begin to deviate. The difficulty is that gravity has only been directly tested down to scales of roughly 1/10 of a millimeter. Below that, the force is so weak, and the experimental challenge is so considerable that deviations would be very hard to detect with the instruments we have built so far. 1/10 of a millimeter is not a small distance by the standards of atomic physics. It is enormous, and yet it represents the current edge of our gravitational knowledge at short range. So an extra dimension smaller than that threshold, smaller than roughly 1/10 of a millimeter, could exist without any experiment yet performed having ruled it out. That is a remarkable amount of room. And the ad proposal used exactly that room. It suggested that if extra dimensions exist at roughly the millimeter scale, the apparent weakness of gravity in our everyday world would have a natural explanation. Gravity would not be intrinsically weak. It would simply be diluted, spread thin across a larger volume than the other forces can reach. What arrives on our brain is only a fraction of gravity's full strength because most of it has dispersed into directions we cannot enter. This would dissolve one of the deepest puzzles in physics, the hierarchy problem. The question of why gravity is so extraordinarily weaker than the other forces, roughly 10 to the 37th power times weaker than electromagnetism. A disparity so vast it has no obvious explanation within the standard framework. The ad model offered a geometric answer. Gravity only seems weak because we are measuring its shadow. A year later, in 1999, Lisa Randall and Raman Sundram proposed a different geometry that addressed the same problem in a different way. Their model also involved 2 branes separated by a gap in a 5-dimensional space. But the extra dimension in their picture did not need to be large. It could be small. What made their model distinctive was the geometry of the space between the branes, not flat, but warped, curved in a specific exponential way. In a warped extra dimension, the strength of gravity is not uniform. It varies from one location to another along the extra dimension, falling off exponentially as you move from one brane to the other. On one brane, gravity would be strong. On the other brane, our brane, in their proposal, gravity would arrive exponentially weakened, not because it has spread across a large volume, but because the curvature of the geometry between the branes has suppressed it. The mathematics of this is precise. Randall and Sundram showed that even a modest separation between the 2 branes, in a space with a specific negative curvature called anti-de Sitter geometry, could produce the enormous ratio between gravity and the other forces that we observe. The extra dimension could be small, and yet the warping of its geometry would do the work that size alone could not. 2 proposals, then, with different geometries and different scales, both offering a quiet resolution to the same ancient puzzle. In one, the extra dimensions are large and gravity is diluted by volume. In the other, the extra dimension is small but curved, and gravity is suppressed by the shape of space itself. Both make predictions. If the ADD model is correct, and extra dimensions exist near the millimeter scale, then gravity measured at sub-millimeter distances should deviate from Newton's inverse square law. The force should strengthen more quickly than expected as 2 objects are brought very close together. Torsion balance experiments, instruments of extraordinary delicacy, designed to measure tiny gravitational forces between small masses, have searched for exactly this deviation. So far, they have found none. The inverse square law holds, as far as these experiments can tell, down to scales of tens of micrometers. which constrains the size of any large extra dimensions to below roughly 50 micrometers. That is not a refutation. It is a boundary. It says that if large extra dimensions exist, they are smaller than this. The search continues, with more sensitive instruments, at shorter distances. And the Randall-Sundrum model makes its own predictions about the spectrum of particles that might appear in high-energy collisions, about the behavior of gravity at scales accessible to particle accelerators, predictions that experiments have tested and continue to test. What both models share is a willingness to take seriously the possibility that the geometry of space is richer than it appears, that the weakness of gravity, which we have simply accepted as a feature of the world, might be a clue, a quiet signal that the space we inhabit is not the whole of space, that somewhere, in a direction we cannot point to, the rest of gravity is still traveling. And the universe, as it always does, keeps its answer just beyond the edge of what we can currently reach. At CERN, beneath the French-Swiss border, a ring of superconducting magnets stretches for 27 kilometers in a circle underground. Inside that ring, protons travel at speeds so close to the speed of light that the difference becomes almost philosophical. They collide, and in the debris of those collisions, physicists read the structure of matter at its smallest accessible scales. The Large Hadron Collider was built for many reasons, but one of them, quiet, patient, written into the design from the beginning, was the search for extra dimensions. The logic is elegant in its simplicity. If extra dimensions exist, and if gravity can travel through them while ordinary matter cannot, then a graviton produced in a collision might simply leave. It would carry energy and momentum into a direction that no detector can reach. And from the perspective of the instruments surrounding the collision point, that energy would vanish. A graviton escaping into the bulk would not announce itself. It would leave only an absence, an imbalance in the books. The total energy going into a collision is known precisely. The total energy coming out should match it. If it does not, if there is a deficit, a gap, a direction in which momentum seems to have gone without arriving anywhere, that is what physicists call a missing energy event. And missing energy events are, in principle, a fingerprint of the invisible. The detectors at the LHC are extraordinarily sensitive to this kind of imbalance. They are built to account for every fragment, every spray of particles, every photon and electron and muon that emerges from a collision. When something is missing, they notice. So the searches were designed, and the data was gathered, and the analyses were run. And as of the most recent published results, no confirmed missing energy events attributable to extra dimensions have been found. The collider has not seen the signal. This is not a failure. It is information. Each null result draws a line. It says that if gravitons are escaping into extra dimensions, they are not doing so at the energy scales the LHC has so far explored. The new geometry, if it exists, is hiding at energies higher than the machine has yet reached, or at scales smaller than the collisions have yet probed. And so the searches continue, at higher energies, with more data, with more refined analyses. The absence of a signal is itself a kind of map, a map of where the answer is not, which slowly narrows the territory where it might be. There is another prediction, quieter and stranger, that some extra-dimensional models carry with them. If the extra dimensions exist at energy scales accessible to a particle collider, then the collisions inside that ring might briefly produce something that has no analog in ordinary three-dimensional physics: a microscopic black hole. The idea requires a moment to settle. A black hole is, in the usual picture, an object of enormous mass, the collapsed remnant of a star, or the ancient accumulation of matter at the center of a galaxy. The black holes we observe in the cosmos are vast, But the threshold for forming a black hole is not about mass alone. It is about density, about concentrating enough energy into a small enough region that the geometry of space curves closed around it. In a universe with extra dimensions, gravity becomes stronger at short distances than it does in 3 dimensions alone. The energy scale at which quantum gravity becomes important, the scale at which space-time itself begins to behave in unfamiliar ways, could be much lower than the Planck energy we calculate, assuming only 3 spatial dimensions. And if that threshold is lower, then the energies achievable in a particle collider might, in principle, be enough to briefly create a region of space so dense that it collapses into a microscopic black hole. It would exist for an almost incomprehensibly short time. Stephen Hawking showed, through a careful combination of quantum mechanics and general relativity, that black holes are not entirely black. They radiate. The smaller the black hole, the faster it radiates, and the faster it evaporates. A microscopic black hole produced in a particle collision would evaporate almost at the moment of its creation, in a time so brief that no ordinary clock could resolve it. But it would not disappear silently. As it evaporated, it would release a spray of particles, a distinctive, roughly thermal distribution of energy spreading outward in all directions. The pattern of that spray would carry information about the evaporation process, and physicists know what to look for. It would be unlike the debris of an ordinary collision. It would have a particular character, a particular signature, that the detectors could, in principle, identify. No such events have been observed at the LHC. Again, this is a boundary, not a refutation. The absence of microscopic black holes places a lower bound on the energy scale at which extra-dimensional effects would become apparent. It says that if the geometry of space opens up into additional dimensions, it does not do so at the energies the collider has reached. The threshold, if it exists, is higher. And there's something worth sitting with in all of this. The LHC is the most powerful particle accelerator ever built. The collisions it produces reach energies that existed in the natural universe only in the first fractions of a second after the Big Bang. And yet, measured against the full range of scales that physics must eventually account for, the energies of the LHC are still modest. The Planck scale, where quantum gravity is expected to become unavoidable, lies many orders of magnitude beyond what any collider built so far can reach. The universe keeps its deepest structure well protected. What the collider has given us, in the absence of signals, is precision, a precise statement of where the boundary lies, a precise constraint on the size and energy scale of any extra dimensions that might exist. These constraints are not nothing. They are the careful, patient work of science, ruling out possibilities, narrowing the space of what remains, building a more accurate picture of what the geometry of space can and cannot be. Every collision that produces no missing energy, no microscopic black hole, no unexpected spray of particles, every one of those null results is a measurement, a real measurement, with real information content. The universe is answering. It is simply answering in the negative. For now, at these scales, and the searches continue. The LHC runs at higher energies with each new operational period. The analyses grow more sophisticated. The theoretical models are refined in response to the data, and new predictions are made, and those predictions are tested in turn. This is the slow, careful conversation between theory and experiment. It does not always produce the answer that was hoped for, but it always produces an answer of some kind. The extra dimensions, if they exist, have so far declined to announce themselves through any instrument we have built. They have not appeared in the torsion balance experiments searching for deviations in gravity at short distances. They have not appeared in the missing energy searches at the collider. They have not appeared in the microscopic black hole searches. And yet, the theoretical reasons for taking them seriously have not diminished. The mathematics remains consistent. The hierarchy problem remains unsolved by simpler means. The geometry of string theory still requires dimensions beyond the three we inhabit. The answer is somewhere. It is simply not yet within reach. And perhaps that is fitting. The dimensions we cannot enter, the directions we cannot point to, the geometry folded into scales too small or energies too high for any instrument we have yet imagined. They remain, for now, exactly what they have always been: quiet, patient, waiting. And so the search continues, not with frustration, but with the quiet persistence that has always characterized the deepest questions in physics. Each null result is a kind of map. It does not show where the treasure is, but it marks, with careful precision, where it is not. And a map of absences is still a map. The absence of microscopic black holes at the Large Hadron Collider is one such marking. If extra dimensions exist at energy scales accessible to the collider, the mathematics suggested that collisions between protons might briefly produce black holes of extraordinary smallness, objects so tiny and so short-lived that they would evaporate almost before they formed, dissolving into a spray of ordinary particles through a process called Hawking radiation. That spray would have a recognizable shape, a particular distribution of energies and particle types that physicists could identify against the background noise of ordinary collisions. They looked carefully and over many years, and at energies that would have seemed impossible to reach just a generation ago. And they found nothing of that kind. Which means that if extra dimensions exist, they are either too small or too tightly curved to produce black holes at the energies the collider can reach. The threshold, wherever it lies, is higher than the instruments have yet climbed. The geometry, if it is there, is folded more deeply than current machines can unfold. But the collider is not the only instrument listening. There is another kind of detector, one that does not search for missing energy or unexpected particle sprays, but listens instead for the faint stretching and compressing of space itself. Gravitational wave detectors. Facilities like LIGO in the United States and Virgo in Italy are built to sense distortions in space-time so small that they make the width of a proton seem vast by comparison. They work by splitting a beam of light along two perpendicular arms and watching for the moment when a passing gravitational wave stretches one arm and compresses the other. The difference in the light's travel time, measured with extraordinary precision, reveals the wave. And gravitational waves carry information that no other messenger can provide. In a universe with only 3 large spatial dimensions, a gravitational wave spreading outward from its source loses amplitude in a specific, predictable way. The wave expands across the surface of an ever-growing sphere, and its strength falls as the inverse of the distance traveled. This is the behavior that general relativity, in 3 dimensions, requires. But in a universe with extra dimensions, the wave would not be confined to that sphere. It would spread into the additional dimensions as well, leaking outward in directions that no ordinary instrument can point toward, and losing amplitude more quickly than the 3-dimensional prediction allows. The wave would arrive at a distant detector slightly weaker than expected, not because it was absorbed or scattered, but because some of its energy had quietly departed into geometry we cannot see. This is a testable prediction. And in the autumn of 2017, an event occurred that allowed physicists to test it. 2 neutron stars, each the remnant of a collapsed massive star, each containing roughly the mass of the Sun compressed into a sphere, perhaps 20 kilometers across, had been spiraling toward each other for hundreds of millions of years, their orbit decaying slowly as they radiated gravitational energy into space. until, at last, they met. The collision was violent beyond ordinary description, and it produced both a gravitational wave and a burst of light. A gamma-ray flash followed by a glow across many wavelengths that faded over days. The gravitational wave was detected by LIGO and Virgo. The light was detected by telescopes around the world and in orbit. Both signals arrived within seconds of each other, from the same point in the sky, from a galaxy roughly 130 million light-years away. That coincidence was itself a measurement. If extra dimensions had been siphoning energy from the gravitational wave during its 130 million-year journey, the wave would have arrived noticeably weakened relative to what the electromagnetic signal implied about the event's true energy. The comparison between the two messengers placed a constraint on how many large extra dimensions could exist. The data were consistent with 3 large spatial dimensions, and inconsistent with certain models that had proposed additional large dimensions through which gravity could freely spread. It was not a discovery of extra dimensions. It was a narrowing, a quiet closing of certain doors, while others remain, for now, open. And there are other messengers still being considered. Particles called neutrinos. Neutrinos are among the most abundant particles in the universe, and among the most elusive. They have a tiny mass, though how tiny is not yet precisely known. They interact with ordinary matter only through the weak nuclear force and through gravity, which means they pass through almost everything without leaving a trace. Trillions of them move through your body every second, arriving from the sun, and you will never feel a single one. Because they interact so weakly, neutrinos are sensitive to aspects of physics that other particles cannot probe, and some physicists have proposed that they might serve as a window into extra dimensions. The reasoning begins with a phenomenon called neutrino oscillation. Neutrinos come in 3 varieties, or flavors: electron, muon, and tau. And as they travel, they shift between these flavors in a regular, wave-like pattern. This oscillation is a quantum mechanical effect, and it has been measured carefully in experiments around the world. But some anomalies in the oscillation data have suggested, tentatively and without consensus, that there might be a 4th flavor, a neutrino that does not interact through any of the standard forces, not the weak force, not electromagnetism, not the strong force, only gravity. This hypothetical particle is called a sterile neutrino. And in the context of extra-dimensional models, a sterile neutrino would be a particle that can propagate not only along our brain, but through the bulk, the higher dimensional space in which our brain is embedded. It would be invisible to every detector we have built, because all our detectors rely on the standard forces. We could not see it directly. We could only infer its existence from the way it affects the neutrinos we can see. A neutrino oscillating into a sterile state would appear to vanish, and then, perhaps, reappear, having briefly traveled through a dimension we cannot enter. Whether sterile neutrinos exist remains an open question. The experimental evidence is suggestive in some datasets and absent in others. The picture is not yet clear, and physicists are careful to say so. The anomalies may have explanations that do not require extra dimensions at all, systematic errors in detectors, or subtle misunderstandings of the neutrino source could account for what has been seen. But the possibility remains that these nearly massless, nearly invisible particles streaming through the earth, through the walls of every building, through the space between your closed eyes and the darkness behind them, might occasionally slip sideways into a geometry we have never mapped, and return, slightly changed, carrying the faintest trace of somewhere else. There is something quietly remarkable about that image. The universe offering its most elusive particles as messengers from its most hidden geometry, not through violence or spectacle, but through the gentlest of deviations, a slight shift in the rhythm of oscillation, a whisper in the data. And physicists, patient and precise, listening for it. The search moves forward, not in great leaps, but in careful steps, each instrument a little more sensitive than the last, each measurement a little more constraining, each null result a little more informative. The geometry, if it is there, is patient. And so are the people looking for it. There is another puzzle that extra-dimensional thinking has been quietly applied to, one that sits at the heart of modern cosmology, like a splinter no one has managed to remove. It concerns the expansion of the universe itself. When astronomers measure the rate at which distant galaxies are accelerating away from us, they find that something is pushing space apart, something built into the fabric of the vacuum, a kind of energy inherent to empty space. This is what physicists call the cosmological constant, and its value is strange. Not strange in the way that unusual numbers are strange, but strange in a way that is almost difficult to hold in the mind. Quantum field theory, the framework that describes particles and forces with extraordinary precision, makes a prediction about how much energy the vacuum should contain. It predicts a value for the cosmological constant based on the contributions of quantum fields fluctuating in empty space. The measured value is smaller than that prediction by roughly 120 orders of magnitude. 120, that is not a rounding error. It is not a small discrepancy waiting to be resolved by a better instrument. It is the largest mismatch between a theoretical prediction and an experimental measurement in the history of physics. A number so far from what the equations suggest that physicists sometimes speak of it in hushed tones, the way one might speak of something that should not exist but plainly does. This is called the cosmological constant problem, and it remains unsolved. Extra-dimensional models offer one possible way of thinking about it. If our universe is a brane embedded in a higher dimensional bulk, then the vacuum energy generated by quantum fields on our brane does not have to stay here. Some of it may leak, flowing out into the bulk the way heat flows from a warm surface into the surrounding air. In this picture, the cosmological constant we measure is not the full vacuum energy of our brane. It is the residue left behind after most of that energy has drained away into dimensions we cannot see. The universe we inhabit would then be, in a sense, a cooled surface. Most of its quantum energy quietly dispersed into a geometry beyond our reach, leaving only the faint remainder that drives the slow acceleration we observe. Whether this is the correct explanation, no one can say with confidence. The mathematics is difficult, and making the leakage work out to precisely the right small value requires careful construction. But the idea has a certain quiet elegance. The vacuum is not overflowing with energy because the extra dimensions are absorbing it. The bulk is doing something we cannot see, and the result is the universe we can. There is another image that appears in extra-dimensional models, one that is stranger still. The possibility of a shadow world. In several brane world frameworks, our observable universe is not the only brane in the bulk. There may be other branes separated from ours by a gap in the extra dimension, each carrying its own matter, its own forces, its own version of physics, entirely invisible to us. Not invisible in the way that dark matter is invisible, present but unlit, but invisible in a more fundamental sense. The particles on a neighboring brane would not interact with our photons, our electrons, our atoms. They would pass through us, and we through them, without any contact at all, except through gravity. Gravity, in these models, is the one force that is not confined to a single brane. It propagates through the bulk, and so it reaches across the gap between worlds. A shadow brane, if it existed, would pull on our brane gravitationally, Its mass would curve the bulk, and that curvature would reach us. We would feel its weight without ever seeing its light. There is something quietly unsettling about that image. A world as complex as ours, perhaps separated from us by a distance measured not in light years, but in a direction we have no name for, detectable only as a slight, persistent tug on the geometry of space. And if two brains can attract each other gravitationally, they can, in principle, move toward each other. Slowly, over vast stretches of time, two brains drifting through the bulk might draw closer, the gap between them narrowing, the gravitational pull between them growing until, eventually, they meet. This is the central image of the ekpyrotic model. Proposed by Paul Steinhardt and Neil Turok in the early 2000s, the ekpyrotic scenario offers a radical reimagining of the Big Bang. In this model, the Big Bang was not a beginning from nothing. It was a collision. Two brains, approaching each other through the bulk over an almost incomprehensibly long period, finally made contact. The energy of that collision was released into both brains simultaneously, filling each with heat and radiation, and the conditions necessary for matter to form. What we call the Big Bang, the hot, dense, rapidly expanding state from which our universe emerged, was, in this picture, the moment of impact. And the universe did not begin at that moment. It had existed before, as a cold, nearly empty brain drifting through the bulk. The collision was not a creation, but a transformation. After the collision, the brains would separate again, pushed apart by the energy of the impact, expanding and cooling, eventually growing cold and sparse once more, until gravity drew them together again for another collision. In this way, the ekpyrotic model proposes a cyclic universe, not a single arrow of time from a singular beginning, but a rhythm, collision, expansion, cooling, approach, collision again. A slow cosmic breath, repeated across durations that dwarf anything we ordinarily call time. One of the persistent puzzles of standard cosmology is the large-scale smoothness of the universe. In every direction we look, the cosmos appears remarkably uniform. The temperature of the cosmic microwave background varies by only tiny fractions of a degree across the entire sky. The distribution of matter, on the largest scales, is nearly the same everywhere. The standard explanation for this smoothness is inflation, a brief period of extraordinarily rapid expansion in the universe's first moments that stretched any initial irregularities to scales far larger than we can observe. The ekpyrotic model offers a different explanation. If two brains approach each other slowly, over a vast period, not in a fraction of a second, but over an immense stretch of time, then the conditions on each brain have time to equilibrate. The slow, gentle approach allows the brain to smooth itself out, to reach a state of near-perfect uniformity long before the collision occurs. The smoothness we observe would then be a memory of that long, quiet approach, not the aftermath of a violent inflationary burst, but the result of patience, of two surfaces drifting toward each other across an almost unimaginable span of time, growing calm in the waiting. The inflationary model and the ekpyrotic model make slightly different predictions about the gravitational waves imprinted on the cosmic microwave background. Future experiments, sensitive enough to detect those faint ripples in the oldest light we can observe, may eventually be able to distinguish between them. That measurement has not yet been made with sufficient precision, and so both possibilities remain open. The universe born in a single, unrepeatable event, or the universe as one beat in an endless cycle of collisions between worlds separated by a dimension we have never entered. Either way, the geometry of what lies beyond our brain, if anything does, would have shaped everything we see: the smoothness of the sky, the temperature of the background radiation, the particular constants that govern every atom and every star. The hidden dimensions, patient and unreachable, leaving their signature in the oldest light. That oldest light carries more than warmth. It carries a question. The cosmic microwave background is not quite like any other light in the universe. It is the faint thermal glow left over from a time roughly 380,000 years after the Big Bang, the moment when the universe had cooled just enough for electrons and protons to settle into neutral hydrogen atoms, and for light to finally travel freely through space without being scattered at every step. Before that moment, the universe was opaque, a dense, hot fog through which no photon could pass unimpeded. And then, gradually, the fog lifted, and light streamed outward in every direction, carrying with it a precise record of the conditions at that instant. That record is still arriving. We detect it today as a faint hiss of microwave radiation, almost perfectly uniform in every direction. Almost, but not quite. Across the sky, there are tiny temperature fluctuations, variations of roughly 1 part in 100,000. And those variations are not noise. They are information, encoded in the oldest light we can observe, a map of the density ripples that would eventually grow into galaxies, into clusters, into the large-scale structure of everything we see. And threaded through that map, at a level of subtlety that current instruments are only beginning to approach, there may be something else. Gravitational waves. Not the gravitational waves from colliding black holes or merging neutron stars, but primordial ones, ripples in the fabric of space-time itself, generated in the earliest moments of the universe and stretched to cosmic scales by whatever process shaped the beginning. If inflation occurred, that rapid, exponential expansion in the universe's first fraction of a second, it would have produced a particular spectrum of these primordial gravitational waves, a specific pattern of amplitude and frequency, imprinted as a faint polarization signal in the cosmic microwave background. The apyrotic model would produce a different pattern, quieter in some respects, shaped by the slow approach of two branes rather than by a sudden, violent expansion. The difference between these two patterns is real, but it is small, and measuring it requires instruments of extraordinary sensitivity, listening for a whisper in the oldest light. That measurement has not yet been made with sufficient precision to decide between them. And so the question remains open, resting in the data we have not yet gathered, in the experiments still being designed, still being built, in the careful, patient work of science moving toward an answer that the universe has been holding since before the first atom formed. If inflation itself occurred within a higher dimensional context, if the rapid expansion of the early universe was shaped or influenced by the geometry of dimensions beyond our three, then the spectrum of those primordial gravitational waves might carry a subtle signature of that hidden geometry, a slight deviation from what a purely three-dimensional inflation would predict. The extra dimensions, if they exist, would not be silent even in the oldest light. They would leave a trace. And yet there is another way that extra dimensions enter the deepest questions of physics, not through cosmology, not through particle colliders, but through a mathematical relationship so unexpected that it took years for physicists to understand what it was saying. It is called holographic duality, or more precisely, the as-CFT correspondence. The name is technical, but the idea beneath it is one of the quieter wonders in modern theoretical physics. In 1997, a physicist named Juan Maldacena proposed that a theory of gravity in a particular kind of higher dimensional curved space, called anti-de Sitter space, is exactly mathematically equivalent to a quantum field theory living on the lower dimensional boundary of that space. No gravity, no extra dimensions, just quantum fields on a flat surface. And yet, the two descriptions, one higher dimensional with gravity, one lower dimensional without it, produce identical predictions for every observable quantity. They are not approximations of each other. They are the same theory, written in two different languages. Since that proposal, tens of thousands of papers have explored its implications. It has become one of the most studied ideas in all of theoretical physics, not because it has been confirmed by experiment in the way a particle detection is confirmed, but because it has proven extraordinarily useful. It has shed light on the behavior of strongly interacting quantum systems, on the thermodynamics of black holes, on the nature of quantum entanglement. It keeps producing answers to questions that were asked in entirely different contexts. That kind of mathematical fertility is itself a kind of evidence, not proof, but a signal that something deep is being touched. And what it touches, at its heart, is the question of dimensions themselves. Because the as-CFT correspondence suggests something that is difficult to hold in the mind without it quietly rearranging things. It suggests that the three-dimensional world we experience, with its depth, its volume, its sense of space extending in every direction, might be, in some precise mathematical sense, a projection, a kind of encoding of information that lives on a lower dimensional surface at the boundary of a larger space. Not a projection in the loose, metaphorical sense, but in the strict sense that every piece of information contained in the three-dimensional interior can be fully described by the two-dimensional boundary, that nothing is lost in the translation, that the interior and the boundary are, in a deep way, the same thing. This is the holographic principle. The name comes from an ordinary hologram, a two-dimensional surface that encodes a three-dimensional image. When light passes through it, the image appears to have depth, to have volume, to occupy space. And yet all of that apparent depth was encoded in the flat surface all along. The holographic principle in physics is something like that, but more fundamental and more strange. It does not say that the world is an illusion. It says something more careful than that. It says that the information content of a region of space is not determined by its volume, but by its surface area, that the boundary, not the interior, is where the full description lives. This was already hinted at in the 1970s, when Jacob Bekenstein and Stephen Hawking showed that the entropy of a black hole, the measure of its information content, is proportional not to its volume, but to the area of its event horizon, the surface, not the interior. That result seemed strange at the time, almost an accident of the mathematics. But it was not an accident. It was an early glimpse of something the AD-CFT correspondence would later make precise. The three-dimensional world we move through, the depth of a room, the distance between stars, the volume of a breath, may be, in some sense, emergent, arising from a more fundamental description encoded on a surface we cannot see and cannot enter. The extra dimension in this picture is not something added on top of the world we know. It is something the world we know may be growing out of. Quietly. The way a shadow grows from a shape it does not resemble. The way a flat page can hold the instructions for something vast. There is no settled answer here. The holographic principle is not a confirmed description of our universe in the way that general relativity is. It is a mathematical relationship, a deep structural hint, a question that has proven too productive to set aside. But it sits at the center of the most serious attempts to understand what space itself is made of, and it suggests, with a kind of quiet insistence, that the dimensions we inhabit may not be the foundation. They may be the surface of something deeper, something we are only beginning, very slowly, to read. And yet, the boundary in this picture does not need to be a physical place. It is not a wall somewhere at the edge of things. It is not a surface you could travel to and touch. The holographic principle is a statement about information, about how much of it a region of space can contain, and where that information ultimately lives. The boundary is mathematical before it is physical, a description, not a destination. This distinction matters because it changes what we are really saying. We are not saying the world is painted on a distant screen. We are saying that the information needed to specify everything inside a region of space is no greater than the information that could be written on its surrounding surface, that the interior, for all its apparent depth and volume, does not contain more than its skin can hold. This is a strange thing to sit with. A room full of air and light and the quiet hum of a sleeping house. All of it, in principle, fully described by something written on the walls. Not approximately, not as a rough sketch, exactly. The first real hint of this came not from string theory and not from holography, but from black holes. In the early 1970s, a young physicist named Jacob Bekenstein was thinking carefully about entropy, the measure of disorder, or more precisely, the measure of how many ways the internal state of a system can be arranged without changing its outward appearance. Entropy, in ordinary thermodynamics, is a property of volume. A larger gas cloud has more entropy than a smaller one because there are more ways to arrange its molecules across a larger space. But black holes presented a problem. If you dropped something into a black hole, its entropy seemed to vanish from the universe. The black hole's exterior gave no indication of what had fallen in. This appeared to violate the second law of thermodynamics, which holds that the total entropy of a closed system never decreases. Bekenstein proposed a resolution that was, at the time, considered almost too strange to take seriously. He suggested that a black hole carries entropy, and that this entropy is proportional not to the black hole's volume, but to the area of its event horizon, the spherical surface beyond which nothing can return. Stephen Hawking, working through the mathematics of quantum fields near a black hole's boundary, arrived at the same conclusion by a different path. He showed that black holes are not perfectly black. They radiate, very faintly, with a temperature that depends on their mass, and the entropy associated with that radiation confirmed what Bekenstein had proposed. The entropy of a black hole scales with the area of its horizon, not the volume enclosed, the area of the surface. This was the first time physics had encountered a situation where the information content of a three-dimensional region was written entirely on its two-dimensional boundary, not as an approximation, as an exact result. And it suggested something quietly unsettling about the nature of space itself. If the maximum information content of any region is determined by its surface area rather than its volume, then in some deep sense the interior is not adding new information as it grows. The depth is, in a way, redundant. Everything that could be said about what is inside is already encoded on the outside. This is deeply counterintuitive. We are accustomed to thinking that more volume means more room for more things. More space means more information. But the Bekenstein-Hawking result says otherwise. It says that space, in this respect, is more like a hologram than a container. That the third dimension does not multiply the information. It only rearranges what the surface already holds. The implications of this reach further still. There is a line of thinking in quantum gravity that asks not just whether extra dimensions exist, but whether the dimensions we already experience are themselves fundamental. Whether three-dimensional space is something the universe has always had, or something that emerges at certain scales. From a structure that is in some sense simpler, this idea goes by the name of dimensional reduction. It appears in several approaches to quantum gravity, including a framework called causal dynamical triangulations, which attempts to build spacetime from tiny discrete pieces and then ask what geometry emerges at large scales. What these approaches find, in various forms, is that the effective number of dimensions is not fixed. It depends on the energy scale at which you are probing the structure of space. At the scales of everyday life, the scales of rooms and mountains and the distances between stars, space appears to have three large dimensions. This is not in question, but as you probe smaller and smaller distances, approaching the Planck scale where quantum effects and gravity become equally important, the effective dimensionality of spacetime appears to decrease. Some models predict that at those extreme scales, spacetime becomes effectively two-dimensional. The third spatial dimension does not disappear in any dramatic sense. It simply ceases to be a meaningful degree of freedom at that resolution. It has not yet emerged. The way that temperature is a meaningful concept for a gas of many molecules, but loses its meaning when you zoom into a single atom, not because temperature was destroyed, but because it was never fundamental. It was always something that arose from something else. The third dimension, in this picture, is something like that. It is real at the scales where we live. It is the depth of a breath, the height of a ceiling, the distance a sound travels before it fades. But at the deepest level of structure, it may be something that crystallizes out of a more basic geometry, the way ice crystallizes from water, taking on a form that the underlying substance did not always have. This is perhaps the most philosophically striking possibility that modern theoretical physics has placed on the table. Not that there are more dimensions than we thought, but that the dimensions we thought we had may not be the bedrock. That space, as we experience it, may be emergent, a large-scale pattern arising from something that does not itself look like space at all. The question of what that something is remains open. Loop quantum gravity builds spacetime from discrete quantum units of area and volume, and the smooth, continuous space of ordinary experience arises only as an approximation, valid at scales far above the Planck length. String theory encodes the geometry of the world in the vibrations of objects moving through 10 or 11 dimensions, and the four-dimensional spacetime we inhabit is one particular low-energy limit of that structure. Causal dynamical triangulations assemble spacetime from pieces and watches what geometry grows. These are different approaches, and they do not all agree, but they share a common suggestion that the dimensions we move through are not given in advance. They are not the stage on which physics happens. They are part of what physics produces. And if that is true, even partially, even as a direction rather than a confirmed result, then the question of extra dimensions becomes something larger than a question about whether there are more of them. It becomes a question about whether dimensions, as such, are fundamental at all. Whether the geometry we inhabit is something the universe chose or something the universe grew. And that question has no clean answer yet. It sits at the edge of what mathematics can currently reach, and what experiments can currently test. It is the kind of question that a field asks when it is still becoming itself. Quietly. The way a mind, drifting towards sleep, holds a thought it cannot quite finish. Not with urgency, just with the soft, open awareness that something is there, just beyond the edge of what can be seen. Loop quantum gravity holds a particular kind of quietness about it. It does not ask whether there are more dimensions hiding somewhere beyond our reach. It asks something closer to home. It asks whether the dimensions we already live in are truly smooth and continuous, the way they appear, or whether, at a scale far too small for any instrument to resolve. They are made of something discrete, something granular. The way a photograph, seen from across a room, looks like a seamless image, but up close reveals itself to be made of individual points of color. In loop quantum gravity, space itself is not a continuous backdrop. It is built from quantum units, tiny, indivisible parcels of area and volume, woven together into the geometry we move through. The smooth, three-dimensional world of rooms and distances, and the space between stars is, in this picture, an approximation, valid at the scales we inhabit, but not fundamental. The fundamental thing is the weave, and the smooth space we experience, the space that feels so obviously, so naturally three-dimensional, emerges from that weave the way temperature emerges from the motion of molecules, not written in from the beginning, but arising, quietly, from something more basic beneath. This is a different kind of strangeness than extra dimensions. It is not about more. It is about deeper. About the possibility that what we take to be the given structure of reality is itself a consequence of something we have not yet fully seen. And it leads, gently, to a question that has been waiting in the background of this whole conversation. Why three? Why are there exactly three large spatial dimensions? Not two, not four, not seven. Three? There's no fully satisfying answer to this in current physics. That is worth sitting with for a moment. One of the most basic features of the world we inhabit, the number of directions in which space extends, does not yet have a clean explanation. It may be that three dimensions are selected by some deep principle we have not identified. It may be that they emerged from some early process in the universe's history. It may be that the question itself is not quite the right one to ask. But there are quieter arguments, suggestions, rather than proofs, that three dimensions are, in some sense, special. Consider what happens in a universe with four or more large spatial dimensions. Gravity, in such a universe, would follow a different law. In our three-dimensional space, the gravitational force between two objects weakens with the square of the distance between them. Double the distance, and the force falls to a quarter. This is the inverse square law, and it is what allows planets to trace stable, closed elliptical paths around a star, year after year, returning to the same point, the same orbit holding. In four large spatial dimensions, gravity would weaken with the cube of the distance, and in that steeper fall, stable closed orbits would not exist. A planet nudged slightly inward would spiral toward its star. A planet nudged slightly outward would drift away into the dark, the precise, repeating paths that allow a world to remain at a stable distance from its sun, warm enough for liquid water, cool enough for chemistry, would not be available. The same instability would affect atoms. The electron's orbit around a nucleus, governed by electromagnetic forces that also follow an inverse square law in three dimensions, would become unstable in higher dimensional space. Atoms as we know them would not hold together. So a universe with four or more large spatial dimensions would be, as far as we can tell, a universe without stable structures of the kind that allow complexity to accumulate over time. And two dimensions. Two large spatial dimensions present a different kind of difficulty. Space becomes a flat surface, and the geometry of that surface imposes severe constraints on what can be built within it. The branching, layered, three-dimensional architecture of a nervous system, the intricate tangle of connections that allows information to be processed, stored, compared, and reflected upon, may simply not be possible on a flat plane without connections crossing and interfering with one another in ways that prevent the necessary complexity from forming. This is a softer argument. less mathematically precise, but it points in the same direction. Two dimensions may not be enough to hold a mind. And this is where a particular kind of reasoning enters the picture, quietly, without fanfare. It is called anthropic reasoning, and it is one of the more philosophically careful tools available to physicists when the usual methods of prediction and experiment reach their limits. Anthropic reasoning holds that the universe we observe is not a random sample of all possible universes. It is necessarily a universe in which observers exist, because only in such a universe could there be anyone to observe anything at all. This sounds almost circular, and in a way it is, but it has a real consequence. If the physical constants of our universe, the strength of gravity, the mass of the electron, the speed of light, had been even slightly different, the structures that allow observers to exist would not have formed. No stable atoms, no long-lived stars, no chemistry, no time for complexity to grow. The fact that we find ourselves in a universe finely tuned for our existence is not, in this view, a coincidence requiring explanation. It is a selection effect. We could only ever find ourselves in a universe compatible with our being here to look. And this reasoning extends to dimensions. We find ourselves in a universe with three large spatial dimensions partly, perhaps because 3 is the number that permits stable orbits, stable atoms, and the intricate architecture of minds capable of asking the question. The string landscape enters here with a particular kind of weight. If the landscape of possible string theory vacua is as vast as the mathematics suggests, something on the order of 10 to the 500 distinct configurations, each with its own geometry, its own compactification, its own effective physical laws, then the fine-tuning of our universe's constants may not require a special explanation in the usual sense. It may simply be that among an enormous number of possible configurations, some small fraction produce universes with the right values for complexity to arise, and we, inevitably, find ourselves in one of those. The precise value of the cosmological constant, the exact mass of the electron, the particular strength of the gravitational constant, these are not, in this picture, the output of a unique and necessary theory. They are the local conditions of the particular vacuum we inhabit, one island in an immense and mostly inhospitable landscape. This is not a comfortable idea for everyone in physics. It feels, to some, like an abandonment of the hope that the constants of nature can be derived from first principles, that there is a reason, a deep and discoverable reason, why the universe is exactly as it is. And that discomfort is honest. The anthropic argument does not explain the landscape. It does not tell us why the landscape exists, or why any vacuum is realized rather than none. It only says that, given the landscape, our presence here is not surprising. Whether that counts as an explanation depends on what you think an explanation is for. And that question, like so many of the questions this night has moved through, does not resolve cleanly. It opens the way a room opens when the last light goes out and the darkness becomes, slowly, something restful rather than something absent. 3 dimensions, stable orbits, a mind that can hold the question, all of it resting, for now, in the quiet, and yet the quiet does not close the question. It only holds it. The way still water holds the reflection of something vast above it. We have been moving through the idea that our universe, its forces, its particles, its particular weight of gravity, may not be the only possible arrangement. That the extra-dimensional geometry folded beneath our 3 large dimensions could have taken a different shape, and that a different shape would have produced a different world. Each stable configuration of that hidden geometry is what physicists call a vacuum, not emptiness. but a settled state. A resting arrangement of the extra dimensions, locked into a particular curvature, a particular topology, and from that locked shape, a complete set of physical laws emerges. The mass of the electron, the strength of the nuclear forces, the precise value of the cosmological constant, all of it flowing from the geometry of dimensions too small to see. The landscape of string theory may contain something like 10 to the power of 500 of these vacua. That number is worth sitting with for a moment. 10 to the 500. There are roughly 10 to the 80 protons in the observable universe. 10 to the 500 is so much larger than that. It is difficult to find a comparison that does not simply dissolve into abstraction. Each entry in that landscape is a self-consistent universe with its own rules, its own table of elements, or something like elements, its own version of chemistry, or something that plays the role chemistry plays here. Most of those universes would be inhospitable to anything we would recognize as structure. Stars that collapse before they ignite. Atoms that never bind. A vacuum energy so large the universe tears itself apart in the first fraction of a second. And then, somewhere in that immense collection, a small number of vacua where the numbers fall into the narrow range that permits complexity. Permits matter to clump and cool and eventually, over billions of years, to think. This is the landscape. And the idea that we inhabit one of its rare hospitable corners is not, by itself, a prediction. It is a context, a frame within which the question of why our constants are what they are becomes, perhaps, less mysterious, or perhaps simply differently mysterious. The word that often appears here is multiverse. Though that word covers more than one idea, and the ideas do not always agree with each other. In some versions, the multiverse is a collection of distant regions of the same space-time, each having undergone a different outcome during inflation. In others, it is the branching structure of quantum mechanics, every possible measurement outcome persisting in its own branch. In the string landscape version, it is the collection of all realized vacua, each a universe with its own geometry and its own physics. These are distinct proposals. They share a name, and they share the quality of being very difficult to test directly. But they are not the same idea wearing the same coat. And it is worth holding that distinction gently, not collapsing them into a single image. Because the details matter, even when the details are this far from anything we can touch. What connects them, what connects all of this, is the original intuition that Kaluza carried to Einstein in 1919. That geometry is not merely the stage on which physics happens. That geometry is physics. That the shape of space, including dimensions we cannot walk through, determines the forces we feel and the particles we are made of. That intuition has never really left theoretical physics. It has only grown more elaborate, more mathematically demanding, more strange. Supergravity was one of its elaborations. A theory developed in the 1970s that wove together two of the most powerful frameworks physicists had built. General relativity, which describes gravity as the curvature of space-time, and supersymmetry, which proposes a deep symmetry between the two fundamental classes of particles. Supersymmetry holds that every particle we know has a partner, a shadow particle with a different value of spin. The electron would have a partner called the selectron, the quark, a squark, the photon, a photino. None of these partners have been observed, but the mathematical structure of supersymmetry is remarkably consistent. and it resolves certain technical problems in quantum field theory that would otherwise require very precise and seemingly accidental cancellations. When physicists tried to build a supersymmetric theory of gravity, supergravity, they found something unexpected. The mathematics worked most naturally, not in 4 dimensions, not in 10, but in 11. 11 space-time dimensions. 1 of times, 10 of space. In 11 dimensions, supergravity has a unique and elegant form. In fewer dimensions, that elegance fractures. The theory becomes less constrained, less unified. 11 seemed to be the natural home of the idea, and that was striking, because it was a number the mathematics chose, not the physicists. Supergravity in 11 dimensions became a precursor to M-theory, the framework that later unified the 5 competing versions of string theory by recognizing them as different limits of a single deeper structure. And M-theory, as we have moved through earlier in this night, requires exactly 11 space-time dimensions to remain self-consistent. The same number supergravity had already quietly pointed toward. There is something in that convergence worth noticing. Different paths, different starting assumptions, different mathematical tools, all arriving at the same count of dimensions, as though the number 11 is not a choice, but a constraint. Something the structure of a consistent, unified theory imposes on itself. Supersymmetry, for its part, remains unconfirmed. The Large Hadron Collider has searched for the partner particles that supersymmetry predicts. At the energies it can reach, none have appeared. This does not rule out supersymmetry. It constrains it. It pushes the predicted masses of the partner particles higher, into ranges that current instruments cannot yet probe. The theory remains viable, but it is waiting. The way many of the ideas in this night are waiting. Not falsified, not confirmed. Held in a state of careful suspension while the instruments slowly improve and the energies slowly climb. And this is, in its own way, a kind of patience that physics requires. The willingness to carry an idea for decades without resolution. To refine it, to test its edges, to let it sit in the mind without forcing it to a conclusion it has not yet earned. Kaluza waited 2 years just to hear whether Einstein thought his letter was worth reading. Einstein sat with the idea for 2 more years before agreeing to publish. The extra dimension Kaluza proposed was not confirmed, not ruled out, not even fully understood. And yet the idea persisted, grew, became Kaluza-Klein theory, then supergravity, then string theory, then M-theory. Each generation of physicists inheriting the question and carrying it a little further, not because they were certain, but because the mathematics kept suggesting that the geometry of space had more to it than 3 directions. That somewhere, folded into scales far below anything we can measure, or stretched across a bulk we cannot enter, there are dimensions that quietly determine everything. The forces, the particles, the particular weight of the world, and perhaps, in some sense, the particular shape of a mind that can lie still in the dark and ask where space ends. And so, the search continues. Not with urgency, not with the restless energy of someone who expects an answer by morning, but with the quiet, methodical patience of people who understand that some questions are larger than any single lifetime. The search for extra dimensions is, at its heart, a search for a deeper geometry, a geometry that underlies the one we move through every day without thinking. When you reach out your hand in the dark and feel the edge of a table, you are navigating 3 dimensions without effort, without thought. But the question physicists are asking is whether those three directions are the whole of it, or whether they are simply the part of a larger structure that happens to be accessible to hands and eyes, and instruments built from matter that lives on a brain. It is a question that sits at the boundary between physics and something older. The oldest inquiry there is, perhaps, what is space? What is it made of? How many ways can it extend? Philosophers asked versions of this question long before there were equations to carry it, and physicists have inherited it, dressed it in mathematics, and sent it into laboratories and into orbit and into the cold interior of particle detectors, without, so far, a definitive answer. But the absence of an answer is not the same as the absence of progress. Every experiment that finds nothing is still a measurement. This is worth sitting with for a moment. When a torsion balance searches for deviations in gravity at short distances and finds none, when the Large Hadron Collider records collision after collision and sees no missing energy that would suggest a graviton slipping into a hidden bulk, when gravitational wave detectors measure the fading signal of two neutron stars merging and find that the waves weaken at exactly the rate three-dimensional space predicts, each of these silences is informative. Each null result draws a boundary. It says, if extra dimensions exist, they are not here, not at this scale, not at this energy. The new geometry, if it is real, must be hiding somewhere smaller, or somewhere more curved, or somewhere that requires an instrument we have not yet built. And that is not failure. That is the slow, careful triangulation of the unknown. Physicists call it constraining the parameter space, which is a technical phrase for something almost meditative, the patient elimination of where something is not, until only the possible hiding places remain. The universe has been hiding things before. Radio waves were always there, moving through the air, carrying information across distances, shaping the behavior of charged particles in every antenna and every nerve. But until the right instrument existed, they were simply invisible, not absent. Invisible. X-rays passed through human tissue for the entirety of human history before Wilhelm Röntgen noticed, in 1895, that a fluorescent screen across the room was glowing when it had no reason to. Gravitational waves, ripples in the fabric of space-time itself, were predicted by Einstein in 1916 and finally detected in 2015. Nearly a century later, when an instrument sensitive enough to measure a displacement smaller than a proton was finally constructed and aimed at the sky. Each of these was a structure that existed all along, waiting not for the universe to reveal itself, but for us to build the right kind of eye. Extra dimensions, if they exist, may simply be waiting for the same thing, a tool we have not yet imagined, an experiment that has not yet been designed, a measurement that will one day make the hidden geometry as plain as a radio wave seems now. There is no particular reason to think we have already built every instrument the universe requires of us. We are, in the long history of inquiry, still quite early. And in the meantime, there is something worth noticing about the space that surrounds you right now. What we call empty space is not empty. The vacuum, the word itself suggests absence. A kind of nothing is in fact a seething, structured medium. Quantum fields fill every point in space, even the space between atoms, even the space between galaxies. These fields are not calm. They fluctuate constantly, producing and annihilating pairs of particles too briefly for direct observation, exerting pressures that have been measured and confirmed. The Casimir effect, in which two uncharged metal plates placed very close together are pushed toward each other by the quantum vacuum between them, is a laboratory demonstration of this. The nothing between the plates is not nothing. It is a field with geometry, with energy, with behavior. And if extra dimensions are real, they are part of that geometry. The shape of the hidden dimensions, whether they are curled into a Calabi-Yau manifold or stretched across a warped bulk, determines the behavior of those quantum fields in the dimensions we can observe. It determines which particles are stable, which forces exist, what values the constants of nature take. The mass of the electron, the strength of the electromagnetic force, the particular rate at which the universe expands. All of these may be, in some deep sense, consequences of a geometry we cannot directly enter. The dimensions we cannot reach may be the very reason the dimensions we can reach have the character they do. This is perhaps the quietest and most profound possibility in all of this. Not that extra dimensions are exotic additions to a world that would otherwise be the same, but that they are foundational, that the three large dimensions we inhabit have the particular properties they have, the particular forces, the particular particle masses, the particular constants, because of the shape of what is hidden. The way a musical note depends not only on the string that vibrates, but on the body of the instrument that surrounds it, the wood that resonates, the air that carries the sound. The note you hear is shaped by structures you are not directly listening to. And so the world you move through, the weight of your body against the bed, the warmth of the air, the faint sounds of a house settling, all of it shaped, perhaps, by dimensions folded into scales so small they will never be felt directly, or stretched across a bulk so vast it will never be crossed. The dimensions we cannot enter may be the very reason that anything as intricate as a mind exists at all. In two large spatial dimensions, the complexity required for thought may simply not be achievable. In four, stable orbits do not form, and stars cannot hold their planets long enough for life to find its footing. Three large dimensions may be, in some sense, the only configuration in which the universe becomes complicated enough to wonder about itself. And so, here, in the particular geometry of three directions, something happened that the mathematics of other configurations may not permit. Matter organized, complexity accumulated, and eventually, after a very long time, something lay still in the dark and asked where space ends. The question has not been answered. It may not be answered in this lifetime, or the next, or for centuries, but it is being asked with more precision than ever before, with instruments that can measure the fading echo of colliding neutron stars, with detectors that can feel the passage of a gravitational wave that crossed 1 billion light-years to reach them, with mathematics that can describe the curvature of spaces no human hand will ever touch. The geometry of the universe is larger than the part we can see. And somewhere in that larger geometry, in the curled dimensions, in the warped bulk, in the hidden structure of the vacuum, may be the answer to why the world is the way it is. Why it has the weight it has, the light it has, the particular silence of a room at night where a mind can grow still and let the question go and rest. There is something worth sitting with before sleep takes you fully. A number: 299,792,458 meters every second. That is the speed of light in a vacuum. And it is not simply the fastest thing we have measured. It is, as far as physics can determine, the fastest anything can be. Not because nothing has tried to go faster, but because the structure of space and time itself does not permit it. To understand why, it helps to let go of the ordinary picture of speed, the picture where faster simply means covering more ground in less time, where, in principle, you could always add a little more. That picture works well enough for a thrown stone or a passing train, but it quietly breaks down long before you reach the speed of light. And the reason it breaks down is not a rule imposed from outside, It is woven into the geometry of time itself. In 1905, Albert Einstein proposed something that seemed almost too simple to be profound. He suggested that the laws of physics look the same to every observer moving at a constant velocity, and that the speed of light is the same for all of them, regardless of how fast they are moving relative to each other. Those two ideas, held together, change everything. If you are moving toward a source of light, and I am standing still, we both measure the same speed for that light, not different speeds, as we would for a sound wave or a thrown ball. The same. That sameness is not a coincidence. It is a constraint on the nature of space and time. To keep the speed of light constant for every observer, space and time must be willing to change, to stretch and compress, to trade one for the other. This is what relativity means, in its quietest form. Space and time are not fixed and separate. They are aspects of a single thing, and they bend together to preserve that one constant. And one of the ways they bend is through time dilation. A clock moving through space ticks more slowly than a clock at rest. Not because of any mechanical effect, not because the clock is damaged by motion, but because time itself, for a moving object, runs at a different rate. The faster the motion, the slower the tick. At everyday speeds, the difference is immeasurably small, but it is real, and it has been confirmed with atomic clocks carried on aircraft and with the precise timing corrections required by satellites in orbit. As an object approaches the speed of light, the slowing of its time becomes more and more extreme. At the speed of light itself, time would stop entirely for the traveling object. This is one way of understanding why nothing with mass can reach that speed. To accelerate a massive object, you must add energy. But as the object moves faster, its effective inertia increases. It becomes harder and harder to push, and the energy required to reach the speed of light becomes infinite. Not very large, infinite. No finite amount of energy is enough. The speed of light is not a barrier that could be broken with a sufficiently powerful engine. It is a horizon built into the mathematics of space-time. Light itself reaches that speed not by overcoming this barrier, but by having no mass to begin with. A photon, a particle of light, does not accelerate to that speed. It exists at that speed from the moment it is created, because it has no rest mass, and the equations that govern massless particles place them, always and only, at exactly that velocity. A photon does not experience time passing. It does not travel through space the way a stone travels through air. It is, in a sense, a disturbance in a field, the electromagnetic field, and the speed at which that disturbance propagates is set by the properties of the field itself, by the electric permittivity and magnetic permeability of empty space. Those two quantities, measured independently, combine to give exactly the speed of light. Maxwell discovered this in the 19th century, before Einstein, before relativity, and it was one of the first hints that light was not simply fast, but fundamentally different. The speed of light is not the speed of a thing moving through space. It is the speed at which electromagnetic influence travels, the speed at which a change in one place makes itself felt somewhere else. And this connects to something deeper still: causality. Causality is the principle that a cause must precede its effect, that information about an event cannot reach a distant place before the event itself has had time to propagate there. The speed of light is the speed of causality, the maximum rate at which any influence, any signal, any piece of information can travel from one point in space-time to another. If something could travel faster than light, it could, in certain reference frames, arrive before it departed, effect before cause, a message received before it was sent. This is not merely strange, it is logically inconsistent in a way that would unravel the coherent structure of cause and effect that underlies everything we call physics. So the speed of light is not just a speed limit in the way a road has a speed limit, it is the boundary of causal connection, the edge of what can influence what. Everything inside your light cone, the region of space-time that light from your current position could reach, is the region you can affect, and the region that can affect you. Everything outside it is, in a precise sense, unreachable, causally disconnected from this moment. The universe is full of regions that will never be in causal contact with each other, not because they are too far apart in space, but because the expansion of space between them is carrying them apart faster than light can cross the growing distance. This is not a violation of the speed limit. The limit applies to motion through space, not to the expansion of space itself. The fabric can stretch faster than light can travel across it, and in the very early universe, it did. But within that fabric, within the causal structure it creates, the speed of light holds. It holds in every medium, though it slows when passing through matter. Light moves more slowly through glass than through vacuum, more slowly through water than through air. But this slowing is not the photons themselves decelerating. It is the light being absorbed and re-emitted by the atoms of the medium, the net effect of countless tiny interactions adding a delay. In vacuum, undisturbed, the speed is always the same. And that constancy is what makes it a constant of nature rather than merely a measurement. It appears in the equations of electromagnetism, of relativity, of quantum field theory. It connects energy to mass through the most recognized equation in physics. It sets the scale at which space and time exchange their properties. It is, in a way, the conversion rate between space and time, the factor that tells you how much time is equivalent to how much distance. And without it, the unified fabric of space-time would have no coherent geometry. So when you lie still in the dark and the room is quiet, and light from a distant source takes a fraction of a second to reach your eye, that light has not simply traveled quickly. It has traveled at the only speed available to something without mass, the speed written into the structure of the fields that fill what we call empty space, the speed that defines the boundary between what can touch what and what must remain forever separate. The universe has a pace, not a rule imposed upon it, a pace that is the universe. And in the stillness of this moment, with no light moving, no signal traveling, nothing accelerating toward any horizon, there is only the quiet geometry of here, and the slow, unhurried rhythm of a mind releasing its hold on the question and resting. And yet, the quiet does not end where the room ends. Beyond these walls, beyond the atmosphere, beyond the last faint traces of air that cling to this small world, space continues. And within that space, woven into its very fabric, there may be more room than we have ever been able to see. Not more distance in the directions we know, but directions we have never moved in. Dimensions folded so tightly into themselves that every point in the universe contains them, and none of us has ever noticed. This is not a new idea. In 1919, a mathematician named Theodore Kaluza wrote a letter to Einstein. He had been working quietly, and what he found was strange and beautiful. He discovered that if you added one extra spatial dimension to Einstein's equations of gravity, something unexpected emerged from the mathematics. Maxwell's equations, the laws governing electricity and magnetism, appeared on their own, without being put there. Einstein held the letter for 2 years. He was not sure whether Kaluza had found something real, or something that only looked real from a certain angle. That uncertainty is worth sitting with for a moment, because it is the honest condition of physics at its edges, not certainty. but careful wondering. Eventually, Einstein helped publish the work. And a few years later, a physicist named Oscar Klein offered a reason why no one had ever seen this extra dimension. It was curled, folded into a circle so small that its circumference was near the Planck length, roughly 10 to the power of negative 35 meters. That number is difficult to hold in the mind. If you took a single atom and expanded it until it filled the entire observable universe, the Planck length, at that same scale, would still be smaller than the atom was before you began. A dimension that small would look, from any ordinary distance, exactly like a point. It would be everywhere and invisible, present in every location in space, and utterly beyond the reach of any instrument we have yet built. The process of folding extra dimensions into compact shapes has a name: compactification. And the shape chosen matters enormously, because the geometry of the hidden dimensions determines which forces and particles emerge in the large dimensions we inhabit. In string theory, the objects that make up reality are not points. They are tiny loops and strands of energy vibrating. And the way they vibrate determines what kind of particle they appear to be. A different vibration, a different particle, the same strand, playing a different note. For the mathematics of string theory to remain consistent, it requires 10 space-time dimensions, 9 of space and 1 of time. The 6 extra spatial dimensions are thought to be folded into shapes called Calabi-Yau manifolds, intricate geometric objects satisfying precise curvature conditions, whose exact form would determine the masses and charges of every particle in the world we can see. The number of possible Calabi-Yau shapes is estimated to be something like 10 to the power of 500. Each one would produce a different universe, different constants, different particles, different possibilities for matter to organize itself. That vast collection of possible configurations is sometimes called the string landscape, and it raises a question that sits at the edge of physics and older kinds of inquiry. If so many universes are possible, why does this one have the particular shape it has? One quiet answer is that we are here to ask. Only certain configurations of physical law permit anything as organized as a mind, and so, whatever the full inventory of possible universes may be, we find ourselves in one that permits us to wonder about the others. There is also a more concrete puzzle that extra dimensions may help resolve. Gravity is extraordinarily weak, roughly 10 to the 37th power times weaker than electromagnetism. There is no obvious reason for this in the physics we know. One proposal is that gravity is not intrinsically weak, but that it spreads into extra dimensions that the other forces cannot enter, diluted across a larger space, arriving in our world already thinned. In Brane world models, our universe is a membrane, a brane, embedded in a higher dimensional space called the bulk. The other forces are confined to the brane, but gravity, being the curvature of space-time itself, leaks through. Lisa Randall and Raman Sundram showed in 1999 that if the extra dimension has a specific warped geometry, gravity can be exponentially weaker on one brane than on another, without the extra dimension needing to be vanishingly small. Gravity has only been directly measured down to scales of roughly 1/10 of a millimeter. Below that, the inverse square law has not been confirmed, and experiments using torsion balances have searched carefully for deviations, finding none so far, constraining any large extra dimensions to below about 50 micrometers. The Large Hadron Collider was designed in part to look for signs of extra dimensions. If a graviton, the hypothetical carrier of gravity, escaped into the bulk during a collision, it would carry energy in a direction the detectors could not see, leaving an imbalance, a gap, a missing piece in the accounting of the collision. No such signals have been confirmed. But the absence is still information. every null result tells physicists more precisely where the hidden geometry, if it exists, must be hiding. Gravitational wave detectors offer another way to listen. In a universe with extra dimensions, gravitational waves would spread into the additional space and lose strength more quickly than expected. The signal from a neutron star merger observed in 2017 placed quiet constraints on how many large extra dimensions could exist. And there are stranger possibilities still. Some models propose that our universe is not alone, that another brane, containing its own matter and forces, floats nearby in the bulk, invisible to us except through gravity, a shadow world, present but unreachable. In the ekpyrotic model, the Big Bang itself was a collision, two branes drifting slowly toward each other across an extra dimension over an immense span of time until they met. The energy of that meeting became the heat and light of a new universe. The smoothness of the early universe, in this picture, comes not from a brief explosive expansion, but from the long, slow approach of two surfaces finding each other in the dark. And then there is the holographic possibility, a mathematical relationship called the ADS-CFT correspondence, proposed by Juan Maldacena in 1997, suggests that a theory of gravity in a higher dimensional space can be exactly equivalent to a quantum field theory on its lower dimensional boundary. The interior and the surface describe the same reality in different languages. In the 1970s, Jacob Bekenstein and Stephen Hawking found that the entropy of a black hole scales with the area of its event horizon, not its volume. Information, it seemed, was being stored on a surface, not in the space it enclosed. This hints at something deep, that the maximum information content of any region of space is determined by its boundary, that what seems like a volume may, in some fundamental sense, be a surface in disguise. The dimensions we experience may not be the most basic level of description. They may emerge the way temperature emerges from the motion of molecules, real and reliable at the scale we inhabit, but not present at the deepest level of the structure. Why three large dimensions? No fully satisfying answer exists, though it is worth noting, quietly, that stable orbits around a star are not possible in four or more large spatial dimensions. The gravitational law in higher dimensions does not permit them. Something about three dimensions allows the long, slow, circular paths that let worlds persist long enough for anything to grow on them. The universe has a geometry, and within that geometry, folded into every point of space you have ever occupied, there may be directions you have never moved in, rooms you have never entered, dimensions present in the stillness of this moment, as present as the dark behind your eyes. The search continues, in laboratories and in mathematics, in the faint patterns of ancient light, and in the trembling of mirrors a kilometer apart. But for now, the question rests. The room is quiet, and the geometry of here is enough.